Fraser Brooks, and he will talk about numerical continuation, which mentioned yesterday from Maciek's talk. Stage is yours.
Thank you very much. Yeah, hi everyone. So yes, I am going to be talking today about numerical continuation, right? This method that we heard a lot about yesterday from Maciek, and specifically I'm going to be talking about the application of numerical continuation to amorphous carbon, right? And I'm sure many of you in this room will not have heard of amorphous carbon. So I've actually got a cute little 3D printed structure of it here, right? Which I'm not going to hand around because last time I did this talk, I did hand it around and everyone was looking at this rather than watching my talk. Right? So you have to watch the talk, but you can look at it afterwards. And what you'll see if you look at this, right, is you'll see that if you look at any individual carbon atom, some of them are in kind of more like diamond-like configurations where they have 4 bonds, and some of them are in kind of more graphite-like configurations where they only have 3 bonds, and they're kind of planar. And so well, what's obvious, right, is there's no crystal structure. There's no kind of long-range crystallography in this structure. It's completely amorphous. And specifically in this talk, I'm going to be talking about amorphous carbon plasticity, right? And then when I say plasticity, many of you, particularly people who have worked on crystals, will think of things like this. So this is a simulation done by someone in my group called Matt and Nasser, and it's looking at the simulation of plasticity in tungsten. And when you have metals, like say when you have a paperclip or something, you bend it back and forth, what's happening is there's the movement of these little defects called dislocations, right? And the net effect of dislocation as it moves through a crystal is to slide one plane of atoms over another. And that's the kind of the mediator of plasticity inside, materials with long-range order, like crystals. But in amorphous materials, like amorphous carbon, there is no crystallography, right? It's completely disordered. And what happens instead when you deform it is not the movement of some large long-range defect. It's actually like very, very small localized plastic events. And you can maybe see that in this simulation here by looking at like these little localized yellow flashes. What those are small plastic events. And the kind of state-of-the-art way to look at these plastic events is a type of simulation, which was mentioned as well by Maciek and also by Lakshmi yesterday, called a quasi-static simulation, right? And the idea of these is you take your simulation box with your material in it, you apply a little strain, right? And then you relax. And you do this over and over again. So you do small strains and relax, and then small strain and relax. And what you see in the case of amorphous carbon is you sometimes see these kind of small localized plastic events in, very often it's just the breaking of a single bond or the forming of a single bond. But then sometimes, and in fact, kind of more regularly as you get to higher strains, you see what I'm going to call avalanche events, right? And avalanche events, just to kind of give you an intuition for it, if you imagine you have your box of amorphous carbon, you do kind of your small shearing steps, nothing's happening, and suddenly lots of things happen all at once in a single quasi-static step. So you get kind of maybe 5, 6, 7 bonds breaking all at the same time, like instantly, right? And between these two types of event, right, they completely characterize the plasticity in these kind of amorphous materials, right? And it's not unique to amorphous carbon. You see this kind of avalanche dynamics in lots of other amorphous systems as well. And I guess the question is, right, how good are quasi-static simulations at actually understanding these kind of events? And in many ways, they are very good, right? They can give you a good indication of the kind of like the statistics, so kind of how often different types of events happen, how big avalanches can get, particularly as you get to higher strains. But what they don't tell you, right, is anything about the energetics of them, apart from the very trivial fact that at the point the avalanche happens, the barrier is 0, right? Like that's all you really know. But before the avalanche happens, you don't know anything about the energy barrier, and you don't know anything about the kind of subsequent events and the energy barriers for those either. And the other thing, which I'm going to focus on kind of later in this talk, is because in a quasi-static simulation, everything happens all at once in the same time step, you don't know anything about the causality of an avalanche. So it doesn't tell you anything about which bond breaks first, and then how those bonds break subsequent bonds, right? And this is something that has kind of just been accepted in the literature for years, that this isn't something that you can really do. And there's only very few attempts to try to address this, right? So what I'm going to argue in this talk is that we can gain some more insight on this using numerical continuation, right? This method that Maciek introduced yesterday. And I have my own little demonstration of numerical continuation, right? Which is maybe less sophisticated than Maciek's demonstration. But it's also only one dimension, but I think hopefully will give you a nice feeling for what's really going on. This is maybe for the non-mathematicians in the room who like looking at pretty pictures rather than equations. So this here is a double well potential, right? This is something that you'll see is very relevant for these kind of amorphous carbon systems. And I've kind of introduced it as a sort of general function, but this function has 2 minima and then 1 saddle point. In this case, it's 1 dimension, so it's just a maxima between the 2. And you can see that as I move this little slider around here, nothing happens, which is and let me just rerun this. Yes, okay. You, hey? Okay, so nothing happens, right? No, something does happen. Try that again. Okay, so you can see as I move the slider around, this function is changing, right? And you can see that the positions of the kind of minima are moving around, the saddle's moving around, you know. And this is a nice sort of, well, I'll show you in a second, this is a nice picture of actually kind of these single bond events in amorphous carbon, right? But let's try and imagine, right, exploring this energy landscape using a quasi-static simulation, right, the kind of state of the art. And what you see when you do that, I have to kind of click away from the bar before I click, is something like this, right? So on the left here, right, what I'm plotting out is the kind of, essentially it's the same x-axis, but the y-axis is this value c on this slider here. And if we imagine that we start in this left-hand minima, and I'm changing c, what you can see is as the minima and the saddle start to kind of converge, we're moving down this branch in our landscape. And at the point where the minima and the saddle collide, in a quasi-static simulation, we'll discontinuously jump from this point over this barrier that no longer exists, and we'll land in this basin on the right-hand side, right? And this is this kind of straight line on this right-hand plot here. And going backwards, we see this hysteretic behavior, right? So we form this kind of hysteresis loop. So we're going to go backwards on our other stable branch, and then when the minima collides on the saddle with the other side, you can see that we discontinuously jump and we land on the branch on the left. And this kind of hysteretic behavior is really characteristic of these, you know, double well potential quasi-static simulations. And as I say, I show you in a minute, it does appear in actually, you know, simulating these amorphous carbon structures. So the question is, right, how does numerical attenuation help us here? What does it do for this landscape? So let's imagine that we're now going to be doing some numerical attenuation. And Maciek introduced it really well yesterday, so I'm just going to talk about how it would be applied to this specific problem. So what we say is we're looking for a continuous solution path, in this case, a continuous path of minima and saddle points, right, ideally, where in order to kind of be able to traverse those saddle points, we form an extended system, which we parameterize by the arc length of the curve S, and we add this extra equation, which just enforces that our solution that we find has to be local to our initial guess, right? And that allows us to kind of like find solutions on these saddle points without, you know, falling back into these minima again. And just to kind of, this constraint equation, this thing at the bottom here, this like intuitively is basically just saying the projection of our initial guess onto the actual solution has to be perpendicular and sort of close, right? That's the idea. So if we were to do this continuation for this, this sort of same example that I just showed you, where we have this hysteresis loop, what you'll see is as I now go downwards in C, if I again start here on the left, when I get to the bifurcation point at the bottom here, where previously it would minimize and drop straight down to the other basin in quasi-static simulations, what happens instead is at the point that the saddles collide, we actually turn this corner, right? And we actually move on to the saddle point. So we're now here, and then we kind of traverse the saddle all the way back to the minima on the other side, like this. And then we go from there onto the stable branch on the other side, right? So kind of back down to the orange. And what this gives us, right? I mean, if you think about it from a kind of energetic energy landscape point of view, right, is it gives us every single point on both minima and also all the points in the saddle. So if we want to find the energy barriers, we don't have to rely on things like non-elastic band methods. We just get all these 3 points for every value of C in this case. And that's like very useful for exploring energy landscapes, right? Okay. So let me find where my PowerPoint is. Okay. So let's then think about a single bond in amorphous carbon, right? The most simple case of where I'm going to show you that this maps quite well into the example I just showed you. So in the case of a single bond, you have your single bond, you're deforming your system, and as you increase strain, at some point that single bond snaps, right? And if we would do that quasi-statically for some single bonds, right? For the single bonds where we go backwards that heals again, we see this, right? Which might look very familiar to what I just showed you, right? It's a hysteresis loop. And if we were to kind of draw lines across this and do non-elastic band simulations on those lines to look at the energy barriers, what you see is exactly this double well potential type landscape, right? Where as you go one way, it kind of, you know, this barrier in the middle disappears, and as you go the other way, it kind of goes in reverse, right? And if we were to plot on the positions of the minima on either side and the saddles, you see that there's kind of clearly a sort of missing middle branch here, right? We could maybe find with numerical attenuation. In fact, it was this figure exactly that I saw in the poster, which kind of brought on this whole collaboration to begin with Ibrahim and Lars, who are the people who kind of simulate these amorphous carbon structures. And when we then run the continuation, what we see is exactly this, right? The continuation turns the saddle and without any real problem at all, kind of finds this middle branch and finds all the maxima, and this is really nice, right? And this is a nice validation immediately that this method works and the energies agree with the neb, etc., right? But this is like the absolute most simple case, right? The case of a reversible single bond plastic event in amorphous carbon. But most of the time, it's more complicated than this. So one level of complication up is an event where it is a single bond break, but it's not reversible. So when you reverse direction and strain, the bond doesn't heal, something else happens first, right? And if you look at the continuation curve for that, you see this, right? So we start off in our initial state, we kind of hit the saddle and minima combine, we turn this corner, and then we kind of end up on this branch forever, right? We never get back to this branch, something else happens first. And we can find this other state by just kind of relaxing off this saddle point. And we can see, if we look at the energy diagram, we can see exactly why this happens, right? Because the well on the other side is far, far lower in energy than our initial state. So there's no way that applying kind of reverse strain heals this bond. I guess with some physical intuition, this would be like if you have a bond in amorphous carbon, you apply some strain, the bond breaks, but it breaks in such a way that reversing the strain doesn't bring those atoms back together again, right? Maybe it lowers that, it makes push them closer, but it doesn't change it doesn't push them back together. So there's no way you can kind of have one single snaking curve which connects the whole thing. And this is nice. And what you can see again is, so these things were done separately. So the nebs, which are the kind of color curves, those agree really nicely with our predictions in energy from our continuation. So once again, this is a nice little validation for, at least in the case of continuation, for these single bond methods.
We tried following both curves much of it.
Yes, oh yeah, of course, right? So what you see is like this go back to quite a lot of strain, and then something else in the system happens, right? So you can imagine that you reverse strain quite a lot, and then the bond over here breaks, which is completely unconnected because you've gone to now quite a different strain, and there's no way this and this never hit, right? And if you go forwards, then you see something else happen, right? It's like you're kind of leaving the local area of your energy surface, I suppose, is one way to think about it. So this is the most simple case, but I guess the real kind of meat of this talk and the interesting question to answer is whether we can use this for actually learn anything at all about avalanches, right? And I'm going to try and argue that we can, right? So let me just show you one more little demonstration on this slide thing. Hopefully it will work this time. So this is it's a very simplified picture of the energy landscape of an avalanche, right? This is obviously, as I say, it's very simplified, but this is kind of a good intuition to have as to what's going on in these avalanche events. So imagine we're in this energy landscape and we start in this left-hand basin here. As we change this value of C, what you'll see is at the point the avalanche happens, which is the point at which this first barrier disappears to zero, this middle barrier, well, this middle basin, which previously existed, doesn't exist, right? So at the point the minimization would happen, if we're doing quasi-static simulations, we're going to jump straight from this first basin all the way down to this final basin, like that, instantly. And this middle basin did exist, so that does correspond to some kind of event, but it's gone, right? It doesn't have, at the point of the avalanche, we don't see it at all. So that is a kind of like a good picture of avalanches. So just to recap, before the event, we have 3 distinct basins, and at the point of the avalanche, we have only 1 basin, right? There is nothing intermediate. And this kind of extends to having, much larger avalanches. And again, this is a very simplified picture, but it's actually it turns out to be quite a good model of these systems. So let's take the simplest case, right? A 3-bond avalanche. So, in this case, it involves these 3 bonds. We're applying a strain, and at some strain, all 3 bonds have an event in the single quasi-static step, right? And the question is, can we unpick the energetics of this event before the avalanche happened, right? So can we find the kind of minimum energy pathway through this event? Can we unpick the causality, so which bond breaks first and how those bonds break each other, right? So the first and most obvious thing to try is a neb, right? Just a nudge elastic band simulation. Would it work directly? And what you find is that with enough images, you can indeed do a nudge elastic band simulation through a whole avalanche like this, right? And this is kind of good in some ways, but there are some kind of very, very obvious downsides to this. The first, you need lots and lots of images because the barriers can be very, very shallow, right? And because you're not doing just one barrier, you're doing multiple, you don't know how shallow they are beforehand, you don't know how different they are. So you need lots and lots of images to make sure you can resolve them, and also to make sure that the application converges. They also, as you get closer and closer to the avalanche happening, nebs stop converging. They start to kind of, some just relax different states. It becomes a real nightmare. And finally, this is just a 3-bond avalanche, right? When you get to kind of 6-bond, 8-bond avalanches, nebs completely fail. You can't do it. But actually, none of these are the main problem, right? Because it turns out the main problem is that it's extremely sensitive to your initial guess of the neb. So my collaborator, Ibrahim, he did a series of nebs where he did different initial biasing guesses. So rather than doing a kind of just linear interpolation between the initial state and the final state as his initial guesses, he actually did like sort of power law initial guesses. So he could different interpolations. And what he found is that he could recover any order of bond breaking in this 3-event avalanche based on his initial guessing, right? So you don't actually know what the right solution is. And in fact, it turned out that the linear one was not the right one in the end for the kind of causality of the avalanche and the minimum energy pathway. So it was essentially not helpful information, right? So let's think about how we could maybe tackle these avalanche problems using numerical continuation. I'm going to go back to this very simplified picture of an avalanche that I had here, and I'm just going to walk through the algorithm that we developed to do this. So the first idea is, right, it starts very similar to the single bond case. So you start off in this, say, left-hand minima here, and you start your continuation, and you do it until this minima and this saddle point collide, right? And at that point, you then move on to this saddle and you start decreasing in strain, right? So you kind of push the energy landscape back towards this kind of structure. So we're on the saddle point, right? And because, as I showed you earlier for the irreversible bond case, it's mostly the case that you then won't, the next event that happens will not be this saddle colliding with this minima, right? In these kind of amorphous carbon systems. So what we do is we actually just relax off this saddle point. We kind of minimize off the saddle point. And by doing so, we can kind of find the adjacent minima on either side, right? And this only works because this system is kind of locally very low dimensional because it only involves generally a single bond snapping. So we can find like the very clear basin on either side of these events. And then once we're here, this intermediate minima at a lower strain, we can repeat, right? We can increase until we find the next saddle, and then we can relax off both sides of that. And the idea is that it's a very simple idea, but we find this actually does generally very well in kind of walking through these avalanche events and kind of finding the actual order of the bonds. Now, there's one more problem, which is that I kind of saw this immediately when I was doing this kind of continuation stuff in these systems. That's that almost all of the time, well, that's not true, about 30% of the time, I saw this in my continuation curves, right? So this is a continuation. Say that I'm breaking a single bond here. This is the point at which we would be turning onto the saddle point. What you see is that the step size has to get so small, so we're kind of changing strain here, that it actually gets numerically unstable and then goes back on itself, and we start to kind of walk back onto the minima again. So it's like an algorithmic failure, like the continuation simply doesn't work. And the reason for that is that because we're changing like the whole strain on the system as our continuation parameter, and we're just looking at the movement of a single bond, the turn is very sharp, and it means that you have to go to very small step sizes to get around these corners. So this was fine for single bonds because, as I say, about 70% of them still worked. But when you're trying to walk through an entire avalanche, which is say like 8 bonds long, right? If 20% or 30% fail, you just can't get through the avalanche. It's just impossible because almost all the time you fail, right? You could do it very occasionally, but it was quite rare. So this was a problem that took us a little while to solve, but in the end, we kind of came up with this method to solve it, where basically you change your continuation parameters. So once you've identified your active low dimensional system, so in this case, right, we know the bond that's breaking here because you can see it quite easily from just like the gradient of the bond, because it kind of approaches infinity at the bifurcation point. So I've identified my bond. We change the continuation parameter from being the strain on the whole system to just being the force on this bond, like an added extra force to this bond. And what that means, right, is it means you can kind of cut the corner in a much easier space. So if you imagine kind of reversing and doing a much simpler continuation with the force, right, what you can do is you can kind of easily walk around this bifurcation point onto the saddle point. And at some point, the force will be back to 0 again, this added force that you're adding to the bond. And that is like when you've re-hit the point on the other side of this curve, right? So then once you're there, you can then continue on that unstable branch. And this only works because we know for a fact which bond's breaking here. So we can kind of just reverse to be very close to this bifurcation point, do this very short kind of corner cutting step in a much nicer space, and then return to this unstable branch, right? And this was like a kind of big breakthrough. And once we kind of got that working, everything worked really nicely. Yes, George.
For the main chunk of the branches, do you still use the stress as the
strain?
yes.
Yes. Yes.
And then you go to the force.
Yeah, just kind of cut the corner just because it's way easy to get around. And then, yeah, and once we're here again, we then return to the strain, right, and we continue. So most of it is still using the strain. It's just to like make it way more stable to get around these kind of really sharp corners. And yeah, and I should say the reason this is necessary is because we're using a machine learning potential and getting Hessian information, which is what you need to get, like to essentially converge around these really difficult points, is really expensive. So we don't want to use it, right? We want to try and use only first derivative information, so just the forces if we can. And this allows us to do that, right? This allows us to still not have to do these kind of expensive Hessians. All right, so here's a 3-bond avalanche, right? Here is a nice continuation curve of us going through it. So these different colors correspond to these different bonds here. And let me just kind of because I'm aware I just put this on the screen without explaining it. Essentially to show you that, so at the point of zero strain there, when it's like 0.00, that's the point where the avalanche would traditionally happen in a quasi-static simulation, right? So we're walking along this curve here, this is our initial state, we get to here, zero strain, and bam, we jump to our final state, right? But with continuation, we can then go on to this unstable branch, corresponding to this first bond breaking. And then once we're here, if we relax, we land here, which just corresponds to only this blue bond breaking. And now we're in a state which is like our kind of intermediate state. And we can do the same thing again. You can see that once we go further enough back, we can then find a state where the green bond hasn't broken as well. Right? So we can kind of resolve it directly into these, let's say these like 3 separate states which have a kind of direct causality between them. Right? And you can't do this with quasi-static methods, and you can't do it with NEBs. So this is kind of novel. And just to show you the energy landscapes through this, so we did do NEBs through these, and this is much easier because we knew the minima, so we could just do single NEBs without having to worry about multiple barriers. You can kind of see how the energy landscape changes as I move this black line along. So you can see here, there's very clear 3 distinct barriers. And as I kind of move it closer towards the point the avalanche happens, you can see this green barrier, particularly here, is almost 0. And then after it, this becomes no longer a barrier, but an inflection point, right? The minima and the saddle have collided, and we're just at an inflection point here. I mean, there's very clearly an inflection point there, but it's no longer a barrier, right? So yeah, it's quite nice, right? It works really well, and the NEBs work really well because we're just doing it between adjacent minima. So that's a 3-bond avalanche, right? We also did bigger ones. So this is a 6-bond avalanche. This is probably the nicest figure I've made on this. It took me quite a while. And you can see that the quasi-static simulation, which is this kind of bold black line, kind of misses everything, right? So you see this whole avalanche, but you don't see any of these intermediate states. But at lower strains, you can see that there is a kind of clear sequence of steps between states, and we have all of the energy barrier information for all of the lower strains for this avalanche, right? Which is pretty nice. I mean, and we get that straight out of the method. So finally, here's an even bigger one, right? It's a really large avalanche now. I'm not going to kind of just get a bit too complicated for me to show these pictures, but I do have a nice little video of this. So imagine we take a line here on this curve, and we kind of shift this line right. I can show you this little video essentially showing you how all of the energy barriers for all of these state transitions fall to 0 as the avalanche happens, right? So as we kind of move, as we kind of increase the strain, you can see that the energy barriers between these different state transitions are kind of falling down to 0. So it's like 1 to 2, for example, would be this line to this line here. And at the point the avalanche happens, which is here, you can see that all of these barriers are 0, and this guy's the last one to fall to 0. And that means that in the quasi-static simulation, you go right around this loop to the final state. But we know that all these intermediate states did exist, right? And this is kind of resolving a big question in this community, because people really care about this. Did intermediate states exist? Is it because your quasi-static step's too big? We know now exactly why, right? They did exist, and the quasi-static step was not too big, because we know exactly what the bifurcation point is. Okay, I think that's it. Thank you very much, everyone. Thank you for listening. Yeah, we have shown this plot. Don't clap yet. I've got a slide. I should have maybe finished with thank you for listening rather than so we've shown it's possible to use numerical integration to separate these cascades into basins and crucially get the full energy barrier information, which is really nice. And we hope that these methods can both kind of help to build maybe high scale models and stuff of these amorphous material plasticity, particularly for amorphous carbon, but then maybe even we could apply them to slightly more complicated amorphous systems as well. So thank you very much, everyone.